In this video, we're going to look at the phase plane and geometric behavior of linear autonomous systems in ordinary differential equations. We're going to explore and make connections between linear autonomous systems and their phase planes. We're going to describe in detail the phase planes for 2D constant coefficient linear systems of the form in which x prime is equal to the matrix A multiplied by x, with x prime is equal to ax plus by, and y prime is equal to cx plus dy. Now in 3.7, we started to talk about the phase plane and the portrait, but we didn't really go into depth, and I said we're going to worry about it later. Now in these sections, we're going to redefine the phase plane and explore the connections that they have to their linear autonomous systems. And some of the possible phase planes we saw in 3.7 look like this. We had this, which is a node and it's unstable. So right here, where these two cross, we are a node and it's unstable. Notice how these vectors are moving away from these two lines. We have a node, and this is asymptotically stable. And that's because, if you notice, the node is coming in. So we're coming in, and some of these are coming in on this side. When I follow this around, it's coming in asymptotically. And also on this side, we are coming in asymptotically. If we take a look at our next example here, we have an improper node that's unstable. Notice from this point right here at the origin, we are coming out. We are swooping out in all directions. And we have an improper node which is asymptotically stable. That was a mouthful. In which you can see we are coming in no matter which way we're going. No matter where we start, we go in toward that point, and they come along crossed as we come in. They seem to come in and coming along that asymptotic type of stability. We have a saddle point, and this is unstable. Notice how I have some that are coming in and some that are going out, and it's going along those lines as we go out. We have a center. This is stable. This is a periodic. So when we think about 3.7, we had some that were periodic. Then we have a spiral that is unstable. We're spiraling out. And then we have a spiral that's asymptotically stable. We're spiraling in, and it seems to be along this axis, give or take. So it's kind of squished. It's like a spiral that's kind of squished. So let's get some definitions here. The definition of a phase plane for the system x prime is equal to f of xy and y prime is equal to gxy is an xy plane with the vectors in which v, the vector v, is equal to x prime of t in the I direction and y prime of t in the j direction, or equivalently, we can write it as f of xyi plus g of xyj. Now this should look something familiar from our Calculus 4 class. These have been drawn at grid points x sub I and y sub I. The set of vectors is said to form a vector field, just like it does in Calc 4, or a directional field for the system. A phase portrait for the system is a phased plane with enough solution curves drawn in to show how the solutions behave in every part of the plane. So an equilibrium solution, that's our next definition, of a two-dimensional autonomous system, x prime is equal to the function f of x and y prime is equal to the function g of y of xy, is a constant solution in which x of t is equal to x bar and y of t is equal to y bar, for which f x bar y bar and g x bar y bar are simultaneously equal to 0. So if we take a look at our predator-prey, we like the predator-prey because it gives us all kinds of information. This is on the phase plane for this system, where I've got x prime of t is equal to f of xy, which is equal to, in this case, x of 2 minus 3x minus 4y, and g prime of t is equal to g of xy, which is negative y plus 3xy. So here's an example of the phase plane. The equilibrium solutions of x prime and y prime are the points x bar, y bar. These are called equilibrium points, fixed points, stationary points, critical points. And where f of x bar, y bar is equal to g of x bar, y bar, and it equals 0. This implies the tangent vector x prime at x bar, y bar is the 0 vector. And if a solution starts at an equilibrium point, it will stay there forever. Since the rate of change in both the x and y is 0, therefore these points in the phase plane represent parametrically an entire solution curve in which we have x of t is equal to x bar and y of t equals a y bar, in which t goes in from negative infinity to infinity. So we need to talk about the existence and uniqueness theorem for two-dimensional systems. We talked about existence and uniqueness theorem before earlier in the quarter. If we have some region R in the xy plane, the system x bar or x prime and y prime satisfies these properties. It has to be. F of x and f of xy and g of xy are continuous everywhere in that region R. And their first partial derivatives, partial derivative of f with respect to x, f with respect to y, g with respect to x, g with respect to y, are continuous. And the way that we define that continuity is like we do in Calculus 3. For all x, y, and r, then given any initial conditions, x of t naught is equal to x naught, and y of t naught is equal to y naught. At some point x naught, y naught, and r, there is a unique solution curve through the point, and it exists for all the point values of t for which the solution remains in R. So phase planes for real eigenvalues. You're like, oh, I love eigenvalues. Thankfully, we get to bring our eigenvalues back in because I thought we'd be done. And the answer is no, you're not done. So you don't have to worry. They're still here for us. They're like our new best friend. We're going to sneak out of the house with our eigenvalues and our eigenvectors. We will now look at the various cases in which we have eigenvalues and their phase plane with equilibrium solutions. There are 6 cases. The first case is when R1 is less than R2, which is less than 0. So in other words, we have them both negative. They're both positive. One's negative, one's positive. One is equal to 0, one is not. They're repeating, and they are non-zero, one repeating value with 2 linearly independent eigenvectors. Now, I think we have done that before, but maybe we haven't. It'll show up if we haven't yet. Now, we know from that section 4.4 that we love so much, that video was like so long, that when A has 2 distinct real eigenvalues, then the general solution of the system can be wrote in this form. X of t is equal to c sub 1 e raised to the r1, where r1 is our eigenvalue, t, and then multiplied by u sub 1, where u sub 1 is the eigenvector associated with r sub 1. C sub 2 e raised to the r2, which is r2 is our second eigenvector, and our second eigenvalue, our second eigenvector is u sub 2. Also, sometimes I use v. Now, here's another theorem. You're like, can't we just get to the examples? Well, we can once we get there. We assume the eigenvalues of A are real. If the line L lies along the eigenvector of A, then its phase plane to any solution x prime is equal to A of x. That starts at a point xy on the line L sub I and remains on L sub I for all of t. That is, as t goes to infinity, it approaches the origin of the eigenvalue r sub I is less than 0, or moves away if r sub I is greater than 0. So in other words, when we looked, you're like, what the heck is going on? When we had all of this stuff up here, and we had these lines, right? They had these lines here, or we had these blue lines here, and here, and here. These are coming from our eigenvectors that are being made from our eigenvalues. So just when you thought the fun was done, it never ends in this class with the eigenvectors and the eigenvalues. Okay, so you can see that I have the u sub I, and this produces this line. And I have this r sub I, r being the eigenvalue, x being up here. So here's our cases. You're like, wow, I get all these cases. And the answer is yes. Good thing you get to have note cards, so that'll make it so much easier. We're going to start with our first case, and with both of our eigenvectors are negative. If both of our eigenvectors are negative, so here's my eigenvector, here's one of them, and here is the other one. My eigenvalues, I should say, not my eigenvectors. So this is going to be made off of, as an example, in this case, happens to be u sub 2, because it's line 2. And this one is formed from u sub 1, because it's line number 1, just like this is line number 2. And they're going to tend to, the solutions are going to go along line 1 and line 2. They're going to go toward 0, 0 as t gets large, even if the solution doesn't lie along either one of these lines. And the direction of the arrows in the phase planes indicate all the solutions are moving toward the origin. It's a stable equilibrium. It's a sink. And this kind of makes sense, right? If you had f of t is equal to e raised to the rt, if r is negative, f of x will decrease as t gets really large. That makes sense when you think about that in our pre-calculus life, when we started learning about e to the rt. Case number 2, where they're both positive, looks exactly like case number 1, except for all the solutions are going to move away. This is going to produce an unstable equilibrium, and it's a source. And then, of course, this makes sense, because if you were to graph on the xy plane, f of x is equal to e raised to the rx, then, of course, as x would go to infinity, this function would be positive and it would grow. It would be increasing. So that makes sense. Now, what happens when I've got one positive and one negative? And I'm talking about my eigenvalues. Well, the line 1 that is associated to the eigenvector of the negative 1, and we have the L2, which is determined by the lambda 2, in this case happens to be positive, then they'll trend toward the origin if the solutions lie along the L1. They will trend away from the origin if solutions are along line 2, because line 2 is positive, trending away from the origin. Again, positive means to move away, negative means to move toward. Now, no matter how close we get to 0, 0, it will move off infinitely as t goes to infinity, unless the solution lies exactly on the line L1. In this case, the origin is unstable. Since all the solutions trend away from it as t goes to infinity, this is called a saddle point. The line L1 is called a separatrix for the saddle point, as we can see in this figure. So let's take a look at what's going on with this figure. So here's an example in which I have my L1 right here. And this is where my r sub 1 is less than 0. And then I have my L2, and this is where my r sub 2 is greater than 0. The next one we're going to look at is case number 4. So you're thinking, how am I going to remember this? On your note card, all you have to do is do a quick little sketch, write all your cases, then it won't be so bad. So when one of them is 0 and one of them is not, if R2 is less than 0, the one that is not 0 is negative, then the solution on the L2, which is formed by the eigenvector associated with the negative lambda, will move towards 0 and along L2. Any other solution not on L2 will run parallel to L2 if it is positive. If the other value is positive and R2 is positive, then the solutions will move away from 0, 0. Now we've got some repeating. When we have R1 is equal to R2 and we have one eigenvector, if my R's, which are equivalent, are less than 0, then the solutions along L, notice I don't have to do L1 and L2 because it's the same eigenvector, will tend towards 0 as t gets large. Any other solutions will trend towards 0, 0 as along L as t gets large. If R is positive, then the solutions will trend away from 0, 0. Notice there's only one eigenvector shown, and the origin is often referred to as an improper node. It is stable if R is less than 0 and unstable if R is greater than 0. So this is what this looks like. Okay. Case number 6. Well, I have R1 is equal to R2, which is equal to R, so it's a repeating eigenvalue. They are two linearly independent eigenvectors that show up. If that happens, then every solution will move along a straight line either toward 0, 0 or away from 0, 0, depending on what R is. So if I'm asked to sketch the phase portrait of the following systems, your first thought is eigenvalues, eigenvectors. I'm so excited. Now, rather than going through it, because we've done eigenvectors and eigenvalues for a while, I'm just going to tell you that my lambda sub 1 is equal to -1, and the vector that's associated to that is -1, 1. My lambda sub 2 is equal to 4, and the eigenvector that is associated to that is 2, 3. And that's pretty much all I need to sketch my directional field. So I put my axes in there. And my first vector, which is V1, is -1, 1. So I'd go -1, 1, and this is the line that's associated to that eigenvector, -1, 1. My second line, which I'll do in red as well, will be 2 in the X and 3 in the Y, so it's going to look something like that. This is L2. So L2, L1. My eigenvector associated with the L1 is negative, so it's going to go along the line and go toward the origin. And L2 is positive, so I'm going to move away from the origin like that. Our general solution, x of t, for this will be c sub 1 e raised to the negative t. I have -1, 1 plus c sub 2 e raised to the 4t, and I have 2, 3 as the vector. Now let's just talk about what I expect this to happen. As t gets larger, e raised to the 4t is going to dominate. It's going to dominate more than e to the negative t. I'm going to ignore the vectors. I know that e to the 4t is going to dominate e to the negative t. So what that tells me is that my solutions, they may run parallel to the L1 or L2, but eventually they're going to scoop out in that direction because the L2 is going to dominate. Because that lambda, which is 4, is going to dominate the lambda, which is -1. And so it's going to have shapes that look something like this. Even if I'm running parallel or almost right on top of, that other one is going to dominate because that e raised to the 4th is going to dominate over e raised to the negative t. So that's the logic behind it, and I didn't have to do a lot of calculations. I just had to think about limits a little bit, like the limit as t goes to infinity, who is going to dominate? Is it going to be e to the negative t, or is it going to be e to the 4t? Well, e to the 4t will dominate. Okay, let's take a look at my next example here. And for my next example, again, I need to know my lambdas because we love them. And we need to find our vectors that are associated with them. So I'm just going to give them to you. So lambda sub 1 is equal to -1. Lambda sub 2 is equal to -6. The v sub 1 is going to be 1, 4. And the v sub 2 is going to be equal to -1, 1. So once again, I'm going to draw my lines based on my vectors. My first vector is 1, 4. So I'm going to go 1, and I'm going to go 4. About right there. So this is my first line. So this is L1. And then I'm going to do my L2 this time in red. So my L2 is going to go -1, 1. So -1, 1. So this is my L2. Now, we know that my -1, the lambda of -1 is associated with the V1, so we're going in to the origin. Probably shouldn't have these arrows on here because that will be a little confusing. I'm just so used to drawing arrows that I want to draw arrows. Now my 6 is also negative. So my lambda, which is 6, is also negative. So these are both going in like this. Oh, I think did I say what this other one was? It was a saddle point. Our previous one was a saddle point, and it's unstable. Should probably have mentioned that one up here. So this is the saddle and unstable. Okay. Distracted. So easy. Squirrel. Anyways, back to this. Now I'm going to write my solution set, x of t, which is equal to c sub 1, not e, c sub 1, e raised to the -t, 1 and 4, and then plus c sub 2, e raised to the -6t, -1, 1. Now, the vector that's going to dominate is actually the -t. The reason is that it's not going to decrease as quickly as this one. So this one's going to dominate. So my solution sets are going to come in. However they come in, they're going to come in and they're going to want to go toward my L sub 1 on both sides, because it's going to be the dominant one. So it's going to look something like that. And this is a node. It is stable and it's asymptotically stable. So that's what that one would look like. Again, no calculations except for the lambdas and the eigenvectors, but whatever. Let's take a look at my next example here. Again, I'm just going to give you your eigenvalue and your eigenvectors. My eigenvalue is repeating, and this time it's only 5. My eigenvector that's associated with it is -1, 2. So I'm going to draw my plane here, and I have my eigenvector, which is a -1, +2. So it's going to look something like this. And I only have one. Excuse me. And it's positive. So I'm going to be moving away from the origin. Now, I haven't yet, and I probably should. Just note that this is my x sub 1 and this is my x sub 2. It's just in case you were wondering. So for this one, we don't really need the solution because we know what's going to happen is that it's going to move away and it's going to just kind of swoop away kind of like that in that kind of motion. Something like that. Not drawn terribly well. I want to go my arrow this way. So it looks something like that. And you're probably wondering, how am I making this decision? Well, what I do is I plug in an easy point. I'll put in 1, 0 into the system. And then I'm going to see which direction the trajectories are moving at that point. And since this point is directly to the right of the origin, the trajectories at that point must already have turned around. And that's how come I know it's going to look like this. They're going to move out here and then turn themselves around. So that's how I knew. Now this is a node. It is unstable, is a degenerate or improper node is what this is called sometimes. Let's take a look at our next example here. Fractions, and you're thinking, I love fractions. Well, I'm just going to give you the eigenvector, which is repeating. This is lambda is equal to -3/2. My eigenvector is going to be -3, 1, which isn't that bad. So once again, I'm going to draw my axes. This is x2, this is x1, and draw my line, which is going to go -3, 1, 2, 3, and +1. So it's going to look something like this. Now I keep wanting to do my arrows, and I shouldn't do my arrows because it can be confusing. So now I'm going to do my arrows in the direction it should be. This is negative, so we're moving toward the origin. I'm trying to figure out which way this is going to go. So what I'm going to do is I'm going to put -1, -1/6. That's what I was talking about in my previous example, is putting in a number to see where it's going. If I multiply this by 1, 0, my answer ends up becoming -1, -1/6. So what this is telling me, and that's a terrible 1/6, what this is telling me is that my trajectories at that point 1, 0 should be pointing toward the third quadrant. So what's happening is that these are coming in like this. And again, these are coming in like this. So these are coming in like this. And so I have this, and this is a improper node, but it is asymptotically stable. Now, let's talk about complex, because that's the only thing we have left to talk about. If we have a complex eigenpair where I have alpha plus or minus beta I, then I have the vector u, and I have the vector vi, then the general solution can be written in this form, which is nothing surprising. We wrote it in this form before. Now notice that we've now cleaned this up slightly, and we said, wait a minute, what's going on here? We have this phi business, the shenanigation with phi. We have this r shenanigator. Well, what r is the square root of c1 squared plus c2 squared. And r cosine phi is equal to c1, and r sine phi is equal to -c2. That will help us look at their phase equilibrium solution, and then there are 3 cases when this happens. When I have a pure imaginary eigenvalue, I have the alpha is less than 0, or I have the alpha greater than 0. Now notice I don't pay attention to the beta, it's just the alpha that I'm concerned with. So if I have a pure imaginary eigenvalue, in other words, the alpha is equal to 0, the phase plane will be concentric ellipses, which does not eliminate circles, as you know, about the origin, and will be periodic with a period of 2 pi divided by p. The equilibrium solution 0, 0 is called the center. The second case, in which my alpha is less than 0, not the beta part, the alpha part, it will still cycle periodically about the origin, but the amplitude decreases exponentially as t gets bigger due to the fact that we have e to the alpha t. The solution curves are concentric spirals that approach the origin, and in this case, it is stable, and we call it a spiral sink. And of course, the last one is, if my alpha is greater than 0, then it's going to be just like this, except for I'm going to spiral outward, and we call it a spiral source. So let's take a look at graphing these phase portraits. My eigenvectors, my first one, is a pure imaginary, and I have 3 root 3 in the I. The v sub 1 that is associated to this would be negative 3 plus 3, the square root of 3i, and that should be a minus between them, and 4. My lambda sub 2 is going to be the negative 3, the square root of 3i, where my v sub 2, of course, is the conjugate of this other one, so negative 3 plus 3, the square root of 3i, and 4. So this is a pure imaginary. That means we're going to have some sort of concentric circles. And I'm trying to figure out how I'd graph this. Well, guess what? I'm going to take my 3, 9, negative 4, negative 3, and I'm going to multiply it by a point, which is 1, 0. When I do this, I get a vector, which is 3, negative 4. Now I'm going to go to the point 1, 0 on my graph. It's about right here. 3, negative 4 is going to point like that. That means at negative 1, 0, because these are going to be concentric ellipses, is going to kind of have that shape. So I might do one other point. I might choose 0, 1 to see what happens. So let's do 3, negative 4, 9, and negative 3. And then let's multiply by 0, 1 and see what I get. And I end up with 9, negative 3. So if I go here, 9, positive 9, and negative 3 is going to go like that. So I think my concentric ellipses are going to have this kind of shape. Poorly drawn. Keep your eyes kind of closed. And, and you can see that these are lovely concentric ellipses going in this direction. And again, very little calculation is needed to get an idea of how these are moving. And this, of course, is a center, and it is stable. Let's take a look at our next example. Now, all I did for the first example is I really didn't use the lambdas or the vectors necessarily to help me decide how it was going to move, simply because I had no real part. I just had the complex part. I still need to find my eigenvectors and my eigenvalues. I still need to do that calculation, so I'm going to do that really fast, and I'll tell you what these are. So my lambda is equal to, I get 2 plus or minus 8i, and my 2 eigenvectors, if I use the lambda 1, is equal to 2 plus 8i. The eigenvector that is associated to that is 1 plus 8i and 5. My lambda sub 2, which is the complex conjugate, 2 minus 8i. Its vector that's associated to this, so this is v1, is going to be 1 minus 8i, 5. This is my v2. And once again, x sub 2, x sub 1. I am probably going to do some matrix multiplication and see where it's going. So I'm going to put in this case, I know that, so even before I start, I know that my lambda is equal to an alpha plus or minus a beta. My alpha is positive, so I know I'm going to expect to spiral out because alpha is positive. My alpha is 2, which is greater than 0. That tells me I'm going to spiral out, and I know I'm going to spiral because it's complex. So now it's just a matter of how am I going to spiral out. So again, I'm going to take the 3, negative 13, 5, and 1, multiply it by the point 1, 0. So here's where I am. When I get done with this multiplication, I get 3, 5. So remember, I am spiraling out. And this confirms it. So I'm going to go 3 in the x and 5 in the y, so it's going to look something like that. So I know I'm going to spiral like this. Concentric spirals out. So maybe I should probably get some more spirals in there. I probably should choose a couple of more points to see that I'm spiraling out like that. And it's just going to continue to spiral out, and it's going to go outward like that. Spiraling out. Anyways, that's it. Not bad. Not bad. Now let's look at our last bit of information that you may find helpful. It's called the trace determinant plane. For any two-dimensional constant coefficient linear system of this form, the type of equilibrium and the point of the phase plane can be completely determined from the values of the trace and the determinant of A without having to solve any of the eigenvalues and eigenvectors. I know. That makes you so sad. Now, I do have to make a couple of corrections in this chart. So the first thing we need to make a change on is this determinant should be 0. This is actually arbitrary as well. So the trace can be arbitrary. It could be positive, it could be negative. The determinant, when they're the same, will be positive here and positive there. It'll be positive here and negative there. And then these are zeros. So make note of that on your notes. This is the summary of everything up above. This is referred to as a trace determinant plane. The ordered pair here that you see is referring to the first being the determinant and the second being the trace. So I have a negative determinant, a negative trace. It's down here in the saddle point area. If I have a positive determinant but a negative trace, I'm down here in the saddle area. This dashed line here represents when I have repeated eigenvectors. And let's just grab this one. My determinant is positive, my trace is positive, my determinant of A is greater than the trace of A squared divided by 4. We are in a spiral and it is a source. So this summarizes the chart up above. So you don't really even need the chart up above if you have this lovely diagram. And that's it for this section, these two sections actually.